Assalamualaikum. My name is Aksar Shafiq Ahmed, roll number 21TE08. Welcome to today's videos where I will tell you about adaptive filters. Adaptive filters are indisciplined tool in signal processing capable of dynamically adjusting their parameters to optimize performance in changing environments. Joining Join me as we explore what adaptive filters are, how they work, and their diverse applications across various fields. So the first question is, what are adaptive filters? Adaptive filters are digital filters designed to automatically adjust their parameters based on the characteristic of the input signal. So these adaptive filters have a capability that allows them to maintain optimal performance even as signal conditions change over time. Unlike traditional fixed filters, which have predefined coefficients that do not change, adaptive filters continuously adapt their coefficients to achieve the desired output. Next is, what is the purpose of the adaptive filters? The primary purpose of adaptive filters is to enhance signal processing efficiency in environments where traditional fixed filters may struggle due to very single characteristic. So by adjusting their parameters in response to changes in the input signal, these adaptive filters ensure that the output signal meets specific performance criteria such as minimizing error or maximizing signal to noise ratio. Importance and application of an adaptive filter in dynamic environment fluctuates. Adaptive filters play a crucial role. Here are some key applications where adaptive filters are widely used. Dynamic environment. We should know what is dynamic environment or adaptive filters, how they work in an dynamic environment. So adaptive filters are essential in scenarios where signal properties are not static. They ensure consistent performance by adapting to change in signal conditions, making them suitable for application where signals were unpredictable. Key applications. Adaptive filters are used in various applications. Some of them are, first one is telecommunication. Telecommunication adaptive filters improve signal quality and reduce interference in communication network. For example, in wireless communication system, adaptive filters adapt to varying channel conditions to maintain reliable signal transmission. Audio processing. Second application is audio processing. Here they enhance sound quality by reducing background noise and removing echoes in audio recording and live communication. For instance, in hand-free communication system or voice assistant, adaptive filters eliminate echo to ensure clear and intelligible speech. Medical devices. Adaptive filters enhance the accuracy of biomedical signals like ECG or EEG, ECG electrocardiogram, and EEG electropherogram by filtering out noise and artifacts. This improves diagnostic accuracy and enables continuous monitoring of physiological signaling in health settings. Now moving towards the basic concept of adaptive filter. So we will define it as adaptive filters adjust their coefficients or parameters based on the input signal so that we can achieve a desired output. This dynamic adjustment aims to minimize error and optimize signal processing efficiency. The ability to adapt to changing signal conditions distinguish adaptive filters from traditional fixed filters. Now moving towards the basic components of the adaptive filters. The core components of adaptive filters include filter structure. This typically consists of tabs or coefficients that adjust in real time based on the adaptation algorithm. Error signal, the difference between the desired output and the actual output of the filter. The error signal drives the adaptation processing by providing feedback on how well the filter is performing. Adapt- Adaptation algorithm is also an core component of filters. This is the mathematical procedure that determines how the filter coefficients are updated based on the error signals. Examples of adaptation algorithms include least mean square and least square last square, LMS and RLS, which we will explore in more detail in upcoming. We should know about the adaptation algorithms. So let's move on towards them. Adaptive filters employ various algorithms to update their coefficients. Let's look at two fundamental algorithms. The first one is LMS, least mean squares. LMS is a straightforward algorithm that adjusts filter coefficients to minimize the mean square error between the desired and the actual outputs. It operates by alternatively adjusting the coefficients in the direction that reduces the error signals. Key features Key features of LMS are simplicity and stability. LMS is easy to implement and computationally efficient, making it suitable for applications where real-time processing is crucial. Stability is with an approach choice of step size. LMS can achieve table conversions, although it may require careful parameters turning to prevent divergence. Practical example of LMS is noise cancellation. One practical application of LMS is noise cancellation. In devices like active noise cancelling headphones, LMS algorithms adaptively filter out background noise to provide a clear audio experience for the user. The second one is RLS algorithm, least square least squares. RLS is more advanced algorithm that updates filter coefficients based on estimation of the signal. It minimizes a weighted linear least square cosine function, offering faster conversions and higher accuracy as compared to LMS. The key features of RLS are accuracy and complexity. Accuracy: RLS provides superior performance in rapidly changing environments by quickly adapting to new input data and minimizing estimation error. Second one is complexity. RLS requires more computational resources due to matrix operation involved in calculating the filter coefficients. Example of RLS is echo cancellation. In telecommunication, RLS algorithms are used for echo cancellation. They adaptively filter out echoes caused by signal reflections, ensuring clear and distortion-free voice communication in real-time applications like VoIP. Design and implementation. There are different that are used to steps that are involved in designing adaptive filters. First one is define requirements. Identify specific performance criteria and constraints such as computational resources, latency requirement, and application specific objectives. For example, noise reduction, signal enhancement. Select algorithm. Choose an appropriate algorithm, LMS, RLS, based on the application needs and the computational capabilities available. Third one is initialize the parameters. Set initial filter coefficient, step size for LMS, forgetting factors of RLS and other relevant parameters. Proper initialization is crucial for achieving optimal filter performance. Next one is implementation adaptation. Write code or utilize existing libraries to implement the chosen algorithm in programming environments like MATLAB, Python, or C++. Implementing adaptive filters involves translating the algorithmic logic into executable code that can process real-world signal effectively. Test and validate. Simulate the adaptive filter with real-world signals to validate its performance under different conditions. Adjust parameters as necessary to optimize filter performance and ensure stability over time. Practical consideration. Consider several factors when designing adaptive filters. Computational complexity, that is, LMS algorithms generally have lower computation overhead compared to RLS algorithm. The choice of algorithm should align with the available computational resources and real-time processing requirement of the application. Convergence rate. LMS algorithm may exhibit slower convergence compared to RLS, especially in scenarios where rapidly changing signal conditions. Understanding the convergence characteristic of the chosen algorithms is essential for achieving timely and accurate adoption. The next one is stability. Proper selection and tuning of algorithm parameters, steps that for LMS, forgetting factors of RLS, are critical to ensure filter stability and prevent undesirable behaviors such as divergence. Now let's move towards the application. Let's explore the some practical application of adaptive filters that are widely used. First one is noise cancellation. Adaptive filters are employed in various noise cancellation applications to remove or reduce unwanted noise from signal. For example, ANC headphones use adaptive filters to analyze ambient noise and generate anti-noise signal that cancel out background noise, providing a quieter listening experience for user. For example, A and C headphones. Their operation is on microphone is to capture external sounds which are processed by adaptive filters to generate inverse waves. These inverse waves are combined with the original sound, effectively cancelling out ambient noise and enhancing the clarity of the audio playback. The next one the next one is echo cancellation. In telecommunication, echo cancellation is crucial for ensuring clear and intelligible voice communication. Adaptive filters analyze incoming signals to identify and remove echoes caused by signal reflection, improving the quality of the voice calls in environment with acoustic echoes. Its example is VoIP application. Adaptive filters in VoIP applications analyze incoming and outgoing voice signals. They adaptively filter out reflected signals from far end, ensuring that users hear clear and echo communication during voice calls. Biomedical signal processing. Adaptive filters plays a vital role in enhancing the quality of the biomedical signals such as ECG and EEG by filtering out noise and artifacts. This improves the accuracy of medical and diagnostic and enable continuous monitoring of physiological signal in healthcare settings. For example, ECG noise filtering. Adaptive filters dynamically adjust to remove power line interference, muscle noise, and other artifacts from ECG signal. This ensures clean and reliable signals for healthcare professionals to accurately analyze heart rate and time information. Thank you for joining me on the exploration of the adaptive filters. We have covered what adaptive filters are, how they work, key algorithms like LMS, RLS, their design and implementation considerations, practical applications across different industries. Thank you, and that's all from my side.